with the next part. But before that, just to address some of the questions, I think first of all is the 3-inch for the HDMI. Okay, so I realize I've been looking at the wrong thing. Uh, if you look over here, we are talking about length for the longest section. Okay, so if you click on this trace here, you can see that at the bottom it divides that trace whereby it has different sections, right? Different sections to make up that long trace. So 1547.9 is just one part of that long trace, right? Just one section. If you want to look at, the overall length, is either to add everything up, or I managed to find an easier way because our trace included this after capacitor trace. You just have to highlight both of them. This will read out the total length of both traces, and then it will give you about approximately 3 inch. Okay, so
Mm.
this will be the correct total length of the trace. So that's first part. Second part is on ground bounce, which I will introduce more later, but to just briefly show you, we have our, let me see if we can make it full screen. Yeah, so basically this is a new feature by our Power Integrity Pro. Basically, we have a dynamic sync ground bounce. So basically, we have introduced the Power Integrity Dynamic Sync Ground Bounce Analyzer. What it does is that basically there is a aggressor power nets and a victim power nets, and then we kind of analyze the ground bounce at different area, and then you can kind of sort of study how much the impact of ground bounce that is from the aggressor to the victim and so on. I'll touch a little bit more about that. This is just a brief one slide to just show you. We'll talk a little bit more about that later on the setup and everything. Okay, so moving on, the next part we're going to talk about would be on channel simulator, okay, which is this part. Okay, so we are at slide number 48, looking at your materials. But I'll skip to this slide because of we have already gone through at the beginning of the session whereby we're talking about basically eye diagram, how eye diagram initially was clean, how it actually propagates through the channel and become a closed eye, all right? And then this is the receive PRBS at the receiver. And then we also talk about, how eye diagram is created, looking at 2UI and then overlay them and this create the eye for us. All right. So we're going to look at channel simulator, whereby we'll be adding in, some of the transmitter and receiver model and kind of understand whether do we get, whether our HDMI channel is it working properly or not. So we are now at slide number 52. So this is some of the anticipation that we have earlier on, for SDD21, SDD11. Those are the results you kind of expected. What is the delay? And, basically based on the EM simulation results we get, we should be kind of expecting an open eye, but let's see. All right, let's see how it goes. So we are going to generate a sub-circuit from SI Pro. All right, so I'm going to go into SI Pro. This part you will need to follow me, or you can refer to slide number 53. So I'm going to go into SI Pro now. All right, and if you refer back to your simulation earlier on, okay, we are looking at your simulation, my HDMI S simulation. If you scroll down to the results tab, you should see a generate sub-circuit. All right. This is a useful feature because it helps to quickly export your EM simulation results together with all the circuit components like the capacitor here we see. It get exported out to schematic so we can hook it up with our transmitter models or even our IBIS AMI model. Okay, so if you can follow me in your SI Pro window, your own HDMI simulation, double click on the generate subcircuit. When you double click generate subcircuit, it should give you a schematic like this. So I'm just going to pause for to make sure everybody's okay. So I just repeat again, just have to double click on generate sub-circuit after your EM simulation results, and then you should be able to see your schematic like this. Okay, so for this schematic, basically what does it contains? All right, first of all, it contains your port setup. All right, remember we set up 4 ports. They are all here. All 4 ports are over here. It contains your schematic of your capacitor model, all right, which is 0.1 nanofarad, if I'm not microfarad. Yeah, 0.1 microfarad. All right, so this has been set up for you. And lastly is your EM simulation results, all right, under a sort of like a S parameter component. Okay, so this, the whole EM simulation from SI Pro has been exported out to schematic. Okay, then, this is the first thing that SI Pro will generate. And then the other thing that SI Pro will generate, all right, if you go back to your ADS main window, okay, let me just put this on top. All right, if you go back to your ADS main window, okay, you should be able to see that there is this my HDMI cell. All right, we call this the cell. If you open it, it's the schematic and the symbol. Okay, so this schematic is actually what you are seeing over here. This is generated for you. And then there is a symbol. If I double click, all right, you should see that it has already assigned the ports. Okay, 1, 3, 2, 4. Okay, this is from the retimer U94, and then this from the FPGA U1. Okay, so basically what this symbol do is that it will represent your schematic over here. Okay, so that's the main reason. Okay, so basically this cell is whatever results that you generate from SI Pro, and then we're going to use it. We're going to use this cell that you see over here to connect it with our transmitter model. So we're looking at slide number 54 now. All right, if you're looking at slide number 54, you can see that we are supposed to open up the lab 2A. Let me just double confirm. Okay, this one, yeah, we can go through them. All right, this is on the single-ended to differential. Again, we can make use of our SI Pro results. All right, so this is on slide number 54. And if you look at slide number 55, it actually instructs you that we can just do a drag and drop to bring in our SI Pro results to the schematic level. All right, so if you look at my screen, basically very easy. This is my sub-circuit. I just have to do a drag and drop. You can see that the symbol starts to appear on my schematic. Okay, and then just hook it up, paste it together. Okay, let me just repeat one more time in case you didn't catch it. In your ADS main window, there should be a my HDMI sim. Just do a click, drag and drop, and then release it, your mouse. Yeah, you probably got to put the main window side by side with the schematic so that it's easier. Okay, so if it's too big, your schematic is taking up full space, just minimize it, make it smaller, and then from the ADS main window, just do a drag and drop, and then you can paste it over here. Okay, so some basic control, if you use your right mouse click and hold, right, this is where you can hand your schematic. Okay, right click, press and hold, then you can pan it. And then zoom in, zoom out is like the mouse scroll. All right, zoom in, zoom out, mouse scroll, zoom in, zoom out. Okay, so this allows you for better control of your schematic. Okay, so once you have successfully done adding in your SI Pro EM simulation results, we can now start to run the simulation. Okay, so on the top bar, you should be able to see a gearbox simulate. This is one way to run the simulation. If you can see it, run it. If you cannot see it, no problem. There should be a simulate tab and there is a simulate button. That's another way. If not, press F7 on your keyboard and then you are able to simulate as well. Okay, so if I run simulate, the simulation will run and excuse me, and then the mixed mode, yeah, the differential results will appear. Okay, and this will be the actual representation of your differential pair results. Okay, I'll just pause for a while. So that's on the mixed mode conversion. So this is one, if you have ADS license with us in the future, this is one way that you can also help to convert your results to mixed mode, especially for any differential pair. Of course, you're working on memory design like DDR, then you don't have to do any mixed mode because DDR is usually single-ended. You can just look at the single-ended results over here. Okay. Okay. So I'll skip a little bit due to time constraint. I will jump straight to channel simulation. Okay, so on your slides, I'm looking at slide number 60. Okay, I'll just jump straight to channel simulation. So if you look at slide number 60, basically in the ADS main window, all right, so this is the ADS main window that I'm looking at. Okay, we'll start to look at Lab 2C. Okay, so Lab 2C channel simulation, you can double click to open up the schematic, and same thing, put the schematic right beside the main window. Okay, so if I double click on channel simulation, right, Lab 2C channel simulation, if you double click, all right, and then put the schematic next to it. Okay, and then what you can do is the same thing. Your SI Pro generated subcircuit, which is my HDI MI sim, you can do a drag and drop and place it over here. Okay, and connect it with your channel over here. So before running the simulation, let me just explain the simulation setup here. Okay, what does the component represent here? So over on the left hand side, what you can see is a transmitter. So basically the transmitter here, if you double click, that's where you can define the bit rate, the high voltage, low voltage, the rise time, fall time, and so on. Basically, your transmitter property, you can define it here. Okay, any encoder that you need, you can define it here. Equalization, like your FRR tabs, is not de-emphasis. All right, those are some equalization. They are part of the FFE. All right. So all this you can define it here as well. Any electrical termination, jitter, uh, crosstalk. All right, crosstalk. I don't think we have time, but this model works as a crosstalk as well. All right, so this is a transmitter model, and then we're gonna just terminate it with 50 ohms for each single end, so total will be 100 ohms. And then for the receiver as well, if you double click, all right, so the receiver will include like CTLE, FFE, DFE for you to try. So for example, for CTLE, if you enable it, we do have some preset. If you click on edit, there are some preset for different standards. For example, like if I scroll down, there should be for like PCIe Gen 4, USB Gen 2, MIPI, and so on, right? So there's some presets for you to apply CTLE. And then likewise, the electrical termination, jitter, all you can include as well. And lastly is the HDI probe. This is where you do your measurement. All right. So the measurement is after the equalization. Okay. So we do the measurement here. And the iProbe does quite a comprehensive analysis. All right. So you can include eye mass, and then you can do measurement like plotting the eye density. If you are interested to look at the eye height, all right, you can always add in the eye height as well. Eye width, some of the basic parameters. You can include there waveform. Those are the things that you can include as well. All right. So quite a lot of measurements that you can done or do in with this iProbe over here. Okay, so we can click on apply if you decided to add more. I think the standard for the template is density. So once you have added in, the last part is channel sim. All right, so this is the simulator we'll be analyzing. So Basically, there are a few modes we do support. Bit by bit is usually the most common modes we see, all right, simulating the number of bits. For now, it's 1000, but I've seen users going up to 1 million bits, right, to get a more accurate results. So it really depends. Statistical is based on, statistical approach to do estimate as well. And then for COM, this is for channel operating margin. If you are working on Ethernet application, right? Where some IEEE standards for Ethernet, then you can use this channel operating margin that we do support as well. This channel operating margin, it does work with MATLAB to provide some of the results. But yeah, basically this COM is, I do see it often for Ethernet application. Okay, so we're just going to simulate bit by bit for 1000 as a simple example. And once your setup is done, again, we can run the simulation to look at the results. Okay, so you can click on the gearbox, press F7 and so on. And this is the eye diagram that you'll be able to see. Okay, yeah, so if you manage to also add in more measurements, like me earlier on in my eye probe, all right, you should be able to also measure like eye height, eye width, and look at the waveform as well. Okay, so what you're seeing here is the data display. Okay, and then you can click. This is something additional. Um, Basically, if I want to look at the eye height and eye width, I can click on this list over here. All right, and then we can do the eye height and eye width measurement. Okay, so this is something additional. I don't think it's on your slide. You can just look at my screen for demo, and then it will calculate, where's the eye height and so on. I think in fact it's better to hold on. We have a summary, right? Once you add in eye height, eye width, there is a summary, all right, that actually lists out, the eye height, eye width, in a visual representation way. Okay, so this is the eye height and eye width of my eye diagram. Any questions for the channel simulation? Okay, no questions. Just want to go a little bit more on channel simulation. So if you look at my screen, on the left, we call it the component palette. All right. And if we look at channel simulation, okay, channel simulation, if you click on it, this is where all the transmitter, the receiver models are. All right. And then one thing I wanted to highlight is your AMI, TX AMI model. Okay. So this is where you insert your IBIS model, inclusive of EMI, I'm assuming, that you get from your vendors. Okay, so let me just quickly do a demo. Let me select an existing file. Okay, let me just quickly search for it. Oops. Okay, so this is an example demo file done by Keysight. It's not an actual vendor component IBIS file, but the IBIS file will contain information like, for example, the electrical property, all right, of your IBIS model. So this is a very simple IBIS model. It should contain, some of the pull up, pull down, ground clamp, power clamp. Those are some of the electrical properties of your model, of your circuits, of the ICs, right? So usually these are provided by vendors, and then we have the EMI model. All right, so this is either provided by vendors, if not, Keysight have solutions to generate EMI models that you need. All right, so this is also included in the EMI model. All right. And then once it's imported, you can see, for example, like the package details, what are the models? I think it's a little bit too big, but what are the pin models that's available, and so on, IV data. This is a very simple IBIS, so there's not much details. The AMI portion, right? So this is where you can apply, I think this is FFE tabs, all right? Number of tabs that you need, gain, and so on. Okay, so just to highlight, for ADS, we do support importing IBCMI models for a more accurate simulation results of your design over here. Okay. And then just to share a bit more things, we are going to look at memory designer later. All right, so this is a standard driven just to share. And then we won't have time to go through other standard driven workflows like PCIe, USB, Internet. But if you're interested, do let Haliatech know. We can always schedule another session. But yeah, we have a lot of standard driven whereby all these features here you can run with a compliance test that's the same with our Keysight instruments, and then you can get a report of your design whether does it meet the compliance. All right. So for example, for PCIe, we are supporting up to PCIe Gen 7 for this release. All right. So yeah, just to share a little bit, we'll look at memory designer later. All right, so yeah, so this is our channel simulation on plotting eye diagram. All right, I think I've gone through what is the setup, the transmitter, the receiver, and also the eye probe that helps to create the eye diagram. The next part, I think I saw a question. Then the next part is on equalization. Okay, so I'm looking at slide number 65 onwards. Okay, so if you are referring to your slides, I'm looking at slide number 65 onwards. And then for this case, we are going to sort of worsen the eye, okay, by exaggerating by gonna add one more block of this subcircuit. So basically times two of the channel to sort of exaggerate to make the eyes a little bit look bad so that we can apply equalization. Okay. So I think to make things worse, we are simulating at 28 gigabits. So we are just really creating a very bad eye to apply equalization. Okay. So some quick rules for estimating loss and eye without equalization. So basically a good representation of whether an eye is good is, basically we hope that is 8 dB or lesser loss at a nice crease rate. All right. So this is one part, and then 75 UI of the eye width. Yeah, we want eye width to be at least 75% of the UI, and likewise for the eye height to be 30%. All right, of the clean eye, I would say. Okay, so these are just some good um rule of thumb. But I think eventually, if you need to meet the standards, right, then it's down to the eye mask again, which we have discussed a lot of time. All right. Usually for standard driven, there are eye masks, which the eye diagram needs to be open and make sure it doesn't overlay with the eye mask. The eye mask is a good measure to know whether your design does it comply with the standards. All right. So IMAS will be even more important way to look at. All right. So it's just a good starting point. All right. So as mentioned earlier, 8 dB loss, 75%. All right. So this should be 75% of your full actual eye. All right. And then 30% of your full actual height. So this might be a good starting point for your design over here. Okay. So I think based on, again, anticipate before you simulate. So I think once we exaggerate some of the settings, we should expect I to be very close. All right. So we're going to simulate that. We're going to look at lab 3A now. All right. So let's go back to ADS main window. All right. So on the slide, we are looking at slide number 72 onwards. All right, so 72, we are looking at channel simulation underscore equalization. Okay, so you can double click on this schematic. All right, so everything has been set up properly for you. Okay, as mentioned, we are going to have, exaggerate things a little bit. The bit rate will increase to 20 gigabits. We're adding in another simulation block, right, to create a bad eye. I think to make it worse, we even have crosstalk introduced. All right, so this is on crosstalk. All right, so crosstalk will be accounted for as well. All right, this is, I think, the aggressor. All right, and then we're going to do a channel simulation. Okay, so you can click on simulate, run the simulation. I hope it doesn't take too long. All right, and then you can see that the eye is quite close, right, based on the results over here. Okay, it's quite close. So this plot you're looking here. Let me explain a little bit. Okay, so this first plot you're looking here is the measurement at the, I think at the die side, right, at the die side. That means before any package or equalization. So this is measurement at the die side. I measure and the eye is very close. And then this is measurement is after any equalization if you have applied it. Okay, so for now we are not applying any equalization. So therefore you are able to see both of the eye diagram are having the same results over here. So that's the results. So now if you go back to the schematic, and the next part is whereby if you look at slide number 73, okay, we're going to apply DFE. Okay, right, so we're going to zoom in into this receiver model, and then you can double click, and we're going to apply our DFE over here. Okay, so I think you just have to click on enable, and basically once it enable the DFE, at least for this generic model, it will sort of optimize the values that's needed for 6-step. Okay, so we're going to apply a 6-step DFE. You'll do some optimization behind the scenes. All right, so you just have to enable it and click OK. Okay, and click OK. So there are some smart algorithm um, in this DFE flow. Okay, and once that's done, we can run the simulation again, and your result should be like slide number 73. Okay, so let me just run the simulation. Yeah, so when after you run the simulation, you can see that after DFE, we are getting a much more open eye. And the optimization approach inside ADS does helps to determine what will be the appropriate values for the 6 steps DFE. All right, and then I mentioned earlier, if you see this kind of edges, this means that DFE is applied. Yeah. Okay, so this is what you're seeing here. Okay, so DFE is one of them. There are many equalizations that I don't think we have time to go through, but just take note it is supported, which you can use for your simulation investigation. Any questions? Everybody can follow? Okay, so the last few parts probably you do not have license for it, but I will just show you. Uh, so this is, if you look at the slides here, we're looking at slide number 75. Probably you can't run it because the next lab talks about IBCMI. All right, you can see over here, which I shown earlier on. In fact, you can even take up the example to look at, no problem. All right. If you are interested, you can open up the lab 3B. There is a PAM4 simulation setup that you can look at. All right, so this is on the IBIS AMI model, which by the AMI actually determine what is the modulation scheme of my signal. In this case, it's PAM4. Yeah, it's either PAM4 or NRZ. All right, so this is something you can configure in the AMI model as well. And so basically, we are simulating the same channel, and you actually hook it up with our Flex DCA probe here. All right, so the Flex DCA probe is actually from our Flex DCA software over here. All right, so for for those of you who have worked with our Keysight oscilloscopes may have probably seen this Flex DCA software. All right, so basically it's the same as ADS as well. Basically, we are leveraging on this software to do some analysis for the eye diagram. All right, so just take note. For ADS, we are able to hook it up with Flex DCA software for it to do this kind of eye diagram measurement, which is the same platform as as our Keysight oscilloscopes over here. So that's on the Flex DCA. And take note, if you look at PAM4, we can simulate PAM4 simulations as well. PAM3, PAM16, we are able to simulate as well. Okay. So that's on the Flex DCA. And then this is for the COM, right? As mentioned earlier, channel operating margin, usually seen in the Ethernet application. So it works with MATLAB behind the scenes. And then this is one example whereby towards the end of the simulation, we will plot out some of the MATLAB plots, looking at the insertion loss. Um, I think there is a common measurement feature in channel operating margin. I think it's called the ERL, effective return loss. I think that's crucial usually in the internet application. So that ERL is also simulated using the channel operating margin. Okay, so this is something that we do support as well if you are looking at internet application. So I think we're done with the first part. We have learned how to sort of look at or bring in a board, all right, and then how we can actually um, run some EM simulation um, using SI Pro, and then how we can actually bring that channel into mixed mode calculation and also performing channel simulation to look at eye diagram and so on. Okay. So these are some of the things that you can work with our ADS tool, at least for the CERDES application. So the first part is very much focused on CERDES. Um, so the flow that we seen earlier on, we discussed a lot on HDMI, but it is applicable for USB, for PCIe, yeah, for any CERDES application, the workflow is applicable to be the same as well. Then I'll move on to the next part, which is on memory. Okay, so what you are seeing here is a server, I think probably a motherboard design for server. Basically on the motherboard, typical components, the CPU, and then of course the motherboard, which then have some DIMM card connected by a DIMM connector. All right, so this is usually the general topology when it comes to memory design. Okay. So looking into further details of how are all these components connected together. Basically for the CPU, we have components like the controller, package, and socket. And then, from the CPU, the signal transmitted to the VRs, the breakout tracers, open field tracers, pin tracers, DIMM tracers. All right. So all these tracers are on the motherboard itself. And then you will hook it up with a DIMM connector, which will then be connected to a DIMM card, all right, and then to the DRAM component itself. So usually, if you talk about IBIS model, usually IBIS model will contain these two parts and the DRAM part, and then of course your PCB will be either the DIMM tracers or the motherboard tracers over here. Okay, so this will be the general topology for your server design. Yeah, so again, I think we are talking about some of the traditional design process which I showed earlier. In the past, what designers does is that they'll create design based on vendor guidance, right? Based on the PC manufacturer, and then they'll fabricate the prototype and then measure and then verify the performance. Okay, and then if there are any issues, they'll go back to the prototype and just manually modify it. All right. Yeah, it's okay, right? That's the flow. Usually they'll just modify it. So if the eye is open, then the designer's job is done here, right? It meets all the standards. But if the eye is closed, then there are so many questions that needs to be addressed. What is the possible cause of a closed eye? Is it due to wrong measurement setup, bulk fabrication incorrectly, not probing, and so on, right? So if it's through the old traditional methods, all right, if you look at DDR3, DDR4, those simple possible root cause that we've discussed earlier, maybe those might help. But for DDR5 onwards, moving into more advanced technology, that's where more things are being included. You might need to really look into DFE tabs, training mode, look back on die termination. Yeah, there's something new for DDR5. All these new things comes in and it makes the whole design even more complex. That's where we propose simulation, whereby simulation you are able to identify issues early. I think as mentioned earlier, and any changes to the design you can change it at the simulation site without um, incurring any costs. All right. So definitely help to save time and able to identify issues properly. So all this I think I've shared it earlier on. I won't go through into much detail. All right. So yeah, any of the possible fixes to the root cause, any possible equalization, you can all quickly do it at the simulation site to see how all these possible fixes can help to actually create or improve your eye diagram over here. Okay, and then yeah, I think moving forward to future DDR6 maybe coming up maybe a few years time. But yeah, as you can see, technology is advancing, speed grades is getting higher, your design margins are getting smaller. The importance of simulation is definitely getting more and more critical over here. Okay, so I think for the lab here, our goal is to build a virtual prototype for this setup over here for our memory design, where it involves a CPU, some of the components of the motherboard together with the DIMM cards. All right, so we're gonna learn how we can actually set this up in our simulation. All right, so this will be a simple overview of our simple server simulation. This is through our memory designer feature. Right, it's a little bit different from the channel simulator that you have seen earlier on. For this memory designer feature, is really dedicated for memory design. Okay, so I'll show you more a little bit. And then I think we'll be using one of the Molex connector, DIMM connector for simulation. And from there, we will actually look at some of the eye diagram plots for your memory design over here. Okay, so we're going to start with DIMM simulation. So let's go to our ADS main window. Okay, so back in our ADS main window, we are going to start with part two, which is on the memory designer side. So if you look at, we're going to first again start with the layout, okay, to do some EM analysis over here. So again, we're going to launch the layout, and you can see this is the DIMM card that's imported either from OTP++ or .vr default. And then I think I've already gone through the same flow. We're going to launch SI Pro. Okay, so I'm looking at slide number 99. If you're following the slides. Okay, slide number 99. So once again, once you have launched it using SI Pro, again, it gives you a 3D view of this DIMM card over here. Okay, and of course, you will have many signal nets, so we'll look into that later. Okay, everybody can follow? Okay. Yeah, so I'm looking at slide number 101 now, if you are following on the slides. So slide number 101, you actually share on how you can set up EM simulation even more quicker with our DDR wizard. Okay, so if you go to tools, sorry, digital standards. All right, it's a bit different now. It's under digital standards. And then we are looking at DDR setup. Okay, so this is a DDR setup wizard whereby you can just click the component on the layout that you're seeing in SI Pro, and then the DDR wizard will actually, plot out the necessary nets for you for the setup over here. If we look at slide number 102, this is where we define the speed grade, the signal voltage, and the rise time. All right, so we're just going to use 3200, but just to share, if you list down the speed grade, you can see that there are different speed grade that you can select over here. So we're going to select the 3200. And basically for the memory controller, you'll be J1 of my component. So J1 is actually this portion of here of my DIMM card, right? This gray portion here, right? Basically this portion here is to connect with the DIMM connector, right? DIMM connector, and then, the signal is actually coming from the transmitter. So the controller will be coming from this J1 component. What you need to do is, just scroll and click on this J1. All right, just click on this J1. Okay, make sure it's highlighted in red. And once you have managed to click on this J1, on the memory controller for the DDR setup, right, click on the arrow. And then J1 will be included into your simulation setup over here. Okay, so that's on slide number 102. Okay, I'll pause for a while, but if you're fast, you can proceed to 103, whereby it starts to include both the U1 and U19 of your DRAM onto devices. Okay, so let me just show you one time on U1. All right, so again, you might need to use right click, press and hold, all right, to drag around your SI probe. Okay, right click, press and hold, and then you can drag, and then this will pan your design over here. Okay, and then to add the memory device, click on U1. Oops. Just be careful. Sometimes it's a little bit difficult to click. Click on U1, right? Make sure U1 is highlighted, and then you can click on memory devices. Okay, so just make sure J1 and U1 are added. All right, you should see some nets being created, but we are not finished yet. Okay, I'll just pause for a while to make sure everybody can follow. But those who are fast, you can look at slide number 104. Okay, whereby it starts to, you need to flip to the back of your DIMM card and then select U19 and add it in. Okay, so you might need to either rotate, right? This is one way which is a little bit painful. Uh, Another way is you can click on this view here icon. There is a back, and then this will bring you to the back of your DIMM card. Okay, this icon over here, there's an arrow. You just have to click back. This will bring you, oh, it's not to the back. Let me see, bottom. Sorry, bottom. Okay, the bottom. Click on bottom, it'll show you U19 nicely over here. Okay, so this is how you can change view. Okay, so this is the top view. And then if I want to change to the bottom view, yeah, this is the bottom view. Where is my DDR setup? Yeah. So in case your DDR setup got closed, you have to go back to the digital standards DDR setup and then click on it. Okay. And then once again, the same thing, select U19 and you can click on the arrow to add in the memory device. Okay. So just take note, memory controller U1, memory devices U1 and U19. Okay, so far okay. Let us know if you need any help. Yeah, I'll just pause for a while. Okay. So this is how DDR Wizard helps you to quickly set up your nets that you want to simulate. So if a little bit, this is where you can sort of configure what you want to simulate. You can disable some of the nets, you can add it in, and so on. Right. So with the DDR Wizard, you'll identify what are the critical nets that is between the controller and the memory device. Right? Even for any of the components, circuit components, all this will be added for you, or rather will be identified for you automatically. So for those who are fast, you can look at slide number 105, whereby you can start to create a DDR analysis. Okay. So to create a DDR analysis, after you have adding J1 and U1 and U19, you just have to generate a DDR analysis. All right. Just click on generate DDR analysis over here, and then you should be able to see a DDR setup that is being created at the setup window. Right. So I'm going to click generate DDR analysis, generate analysis anyway. All right. It's okay. And then you should be able to see the DDR setup at the bottom here. Okay, so again, if you look at this setup over here, there are some warning message. Okay, so I think the most critical one is the yellow exclamation mark, right? So it says that a component model is invalid, right? So what you can do is this resistor. Basically, we need to set up a few things, I think. Let me just take a look. Yeah, we will run the simulation, but basically just to explain. Okay, let me just go to the top. Okay, you can see that this is a parallel resistor. Okay, for this DQ nets over here. Okay, so basically to remove that, you can follow me. I don't think it's on the slides. Yeah, it's not on the slides, but basically you can double click. All right. This will shows you the component model, and we're going to check it as an array component, right? Since there are two resistor within that one component plot, we're going to include it as an array component, all right? And then because it is a resistor, we're going to create a lump, All right, and I think this is 30 ohms. Okay, so in case you're following, we're going to double click on the component. Okay, make sure it's check array component, and then it's 30 ohms. Okay, so this part I won't go through in details. I think this one is very detailed settings, but basically, yeah, we're gonna go run the simulation, but I just run through. We also need to, change the port settings. I think it's been assigned wrongly. So usually I think it's -1, 2, -2, and then 1, -1. Yeah, and then it will change to, give me a minute. Let me see. Yeah. Okay. So basically we have to change the port numbers, all right, because it's an array component. So by changing 1, 2, -2, -1, you will know which port is supposed to be tied to the resistor component. Okay. So this part, yeah, if you didn't manage to do it, it's okay. This part, because we won't do the S parameter, sorry, the SI Pro to take a lot of time. But yeah, to just show you the flow on how easy it is in SI Pro for you to set up your DDR simulation. Okay, that's the main picture of this lab over here. Okay, and then of course, yeah, once you have set up everything, you can do the same, define the frequencies and then start to run the simulation. Okay, so we won't run this simulation because it will take a longer time. As you can see, the signal nets that we are simulating is a lot. Okay, we are going to simulate all this, so it's going to take some time, so we are not going to do that. All right. Okay, so just take note, SI Pro, create an easy way for you to set up memory simulations easily. Okay, that's the key message over here. Okay. So the next part is we are going to simulate the dim traces that you've seen earlier on, right? In fact, we have already done the simulation for you, so we just use the results automatically. So we're going to, use that EM simulation results of that dim traces initial that you've seen earlier on, plug it into our memory designer to do some channel simulation of it. Okay. So let me go to my ADS main window. So I'm looking at slide number 106. Yes, slide number 106, if you're looking at the slides, whereby we are looking at lab 2. Okay, lab 2. So you can double click on lab 2, which will launch the schematic. Okay. So once you manage to launch the schematic, what we're going to do is, for now, we are just going to simulate the dim trace to sort of see whether does it give us an open eye. All right, so mainly just this dim trace portion. All right, so if you look at slide number 107, basically we're going to add in a PCB component to represent our dim traces over here. So how do you do that? On the left, we have our simulation memory designer component palette. Okay, you just have to click on the memory designer component palette, and there should be a PCB component over here. Okay, so you can click on this PCB component, and then you can place it in the middle over here. Okay, so I repeat, there should be a memory designer component palette. Okay, click on this. You should be able to see a PCB component, right, which is, I think, third row, first one, third row, first column, third row. Click and then place it at the center over here. So once that's done, you can double click on the printed circuit board. Okay, and we're going to select SI Pro generated cell, right? Because of the dim card, we use SI Pro to do the simulation. So we're going to select SI Pro generated cell, all right, and then click next. And then we're going to select, yeah, the DDR circuit solution, okay, which we have already simulated for you. Okay, so once that's done, you can click OK or click next. In fact, click next. And you can see that, these are all the signal traces that we have EM simulated, all listed down over here. Okay. So just to briefly explain, I won't go through into much detail, but the key things that you need to understand is on reference designator. Okay, the reference designator will tell you, basically set up the connection. All right, so you can see port and port name. All right, basically this port is connected to J1. All right, so basically those listed in J1, they need to be connected to the controller, which is J1. Okay. I'll show later, but basically the controller have the same reference destination as J1, right? So all this J1 here will be connected to the memory controller. And then if you scroll down, there is U1, right? So basically U1 and U19, okay, they're represented by this DRAM memory over here. Okay, so U1 and U19, they will all be connected to the other side, or rather the output of the DIMM card connected to the DRAM. Okay. So these are the settings, and then of course for different traces, you have the DQ0, DQ1, and so on, right? And then of course data strips as well. So all these are configured for you. You don't have to do anything. You just have to click finish, and then you are done importing the SI Pro results into the schematic. Okay. And then I just want. Oh, sorry. Yeah, just make sure the channel ID is also included already for you. If it's not included, please manually add in all to 0. Okay, we're just going to simulate a single channel for now. Okay, so just make sure the channel ID is all added 0. Okay, and then you can click finish. Okay, so this part we are looking at slide number 108 and 109 and 110 as well. Yeah. Let me pause for a while, make sure everybody is okay. Okay. So we have set up the DIMM card, and then of course we need to set up the controller, right, which is the transmitter and the receiver. So this has already set up for you. If you look at the component palette on my screen, there is a controller component over here, which I placed it over here. And if I double click on it, basically it has already set up the transmitter characteristics that I need. All right, so you can see here, this controller has a J1 reference designator. All right, so this reference designator is important because it will indicate to the simulator how the different components are connected together. J1 must be connected to J1. Okay. So J1 is included, and then if you scroll down and look at the signal property, you can see that we have enabled DQ0 all the way down to DQ7. So 8 bits of DQ signals, and then of course the data strobes as well. Okay, so this will be the setup. Yeah, just enabled it, and then DQ0 to DQ7 with the data strobe will be simulated. Okay, so all these are set up for you. You don't have to do anything. I'm just running through what is set up so that you can have a better understanding of how the simulation is being performed. We can look at the model setup. That also has been set up for you. So this is something that I've seen early on, same as the SEDES. That's where you can define the PRBS mode, the bit sequence, any equalization that you want to apply for your memory design, your jitter, your electrical parameters, your waveform, rise time, fall time, all this you can define it here as well. Okay, so that's for the controller. And then the memory side is the same. All right, if you double click on the memory side, now you can see that both U1 and you can see that J1 is no, okay, N is no, but we enabled U19 and U1. Okay, so U19 and U1, which is the DRAM, it will be considered in the simulation. And likewise, you can see on the signal property U19 and U1, all right, all are being simulated, which will represent the DQ0 to DQ7 together with the data strobes. Okay, so all this, oh, rather the data strobes are not simulated. You can see it's N, right? So you can also configure what you don't want. In this case, I think the data strobe we are not taking into account, just the DQ signals. So this is how you can set up what you want to simulate for the signal trace, especially for memory, which will tends to have a lot of even much more signal traces as compared to the SerDes application. And then the same thing for DQ side, for DRAM side, you can apply the different equalizers, CTLE, DFE, FFE that we have discussed earlier on. All those you can apply it as well. Okay. Okay. So that's the basic run through. The next part is we're going to connect everything up. Okay. So as mentioned earlier, we're going to simulate from DQ0 to DQ7. Okay, so if you think of a manual way, you probably might be thinking, oh, maybe this means that I need to, you know, insert 8 wires, all right, to connect each of the DQs between the controller to the PCB board. Okay, but you don't have to do so because Memory Designer makes it easy. So if you look at slide number 112, okay, slide number 112, we're going to insert a wire to connect the controller and the PCB board. So what ADS is able to do is that we just have to click on the insert wire, place it at the edge of the controller, and hook it up on the edge of the PCB board. Okay, so you get this smart component window appearing after you set up the connection. Okay, I'm at slide 112 if you're referring to the slides. Uh, yeah, so once this smart component window is out, after you have, select these 2 points, I'll just repeat again. Okay, insert wire over here. Okay, you should be able to see an insert wire over here. And then once you have clicked insert wire, just click on the controller edge over here, and then connect it with the PCB edge over here as well. Okay, and then this will have the connect HSD smart component popping up. What you just need to do is just connect all. Okay, as long as the reference destination, the signal ID, channel ID, both the controller and the PCB are the same, uh, Memory Designer is able to connect everything up for you with just a single bus wire. Okay, so just select connect all and click OK. And then there you go. Just one single bus wire represent all the traces that you need to connect. Okay, so Memory Designer here helps you to save time for any complicated or complex simulation setup. Okay, so for those who are faster, you can do the same. All right, we're going to connect up the PCB together with the memory or the DRAM. Right, so again, insert wire and then do the same. Click on the edge of the PCB and then connect it to the memory side. And then click on connect all and press OK. Okay, so everything will be set up for you very quickly. Okay, I'll just pause a while here, just to make sure everybody can follow. Okay, so for those who are done, you might be seeing this ghost wire that you are looking at my screen. To remove them, just press escape on your keyboard and then it will just disappear. Okay, so I repeat, if you are still seeing this ghost cross line on my like is showing on my screen, just press escape and then it will disappear. Okay. Okay, so for those who are done, you can start to run the simulation. Just click on simulate. Here I'm looking at 116. Once you hit simulate, you are able to look at the eye diagram. Okay, so everything has been set up for you very quickly. All 8 eye diagram plots has been plotted out for you. So you don't have to do anything. Just take note that you are able to plot out all the different traces eye diagram together. Okay, so this is from the results you can look at. Okay, so hopefully from here you can see that ADS we do have this kind of smart component to represent multiple transmitter, multiple receiver models, and then the smart bus wire to just have one wire for you to connect everything up together. Right, so this helps you to be efficient, less confusing, less complex when it comes to this kind of simulation setup over here. Okay, so this is just a brief overview look on Memory Designer. Of course, for the full server motherboard design, that's where you will start to include like controller. Sorry, not correct, controller, connector models, which is usually represented in S parameter files that could be provided by your vendors. So we're going to look at how we can actually bring in S parameter model files into the simulation, and then you can connect it up with your PCB board or motherboard as well. Okay. So if you look at the slide, we are looking at slide 118. Basically, from the controller, we're going to hook it up with another connector. So we call this a system simulation. Yep, let's take a look over that. I hope there's no issues. So we can go back to the ADS main window, and then we can double click on the DDR system simulation under schematic. I hope it's working fine because all these are quite old components. Okay, there might be a possibility this schematic might not work, but let's go through the flow. Okay, because I think I've not updated this with the latest version on that. So I apologize for that. But let's go through the flow to just understand how we can bring in S parameter file for connector models. Uh, so I'm looking at slide number 120. Okay, slide 120, whereby on the component palette, you can see that we have a DIMM connector that we can actually use and insert into our schematic over here. Okay, so if you click on the DIMM connector and place it on the schematic. Okay, so I'm looking at slide 120, and if you have placed the connector, we can start to look into slide 121. Okay, so there's a connector model, just place it in the middle. And then we're going to double click on the connector model. Okay. Once you double click on the connector model, I'm looking at slide number 121. We're going to browse for the Molex model. Okay, so click on browse, and then we can see the Molex DIMM model. Okay, and once that's done, you can click open. All right, so you can see that it identifies as a touchstone file. Okay, touchstone file. And then you can click on next once you have included the Molex file. Okay, click on next, and then we can define the reference destination. Okay, so again, the reference destination is to define where the connection to be. All right, so this is out to connector. Okay, I'm looking at slide 122 and then to J1. Okay, so I just pause over here so that you can see what to key in over here. So you can click on next once you have keyed in the reference destinator. Okay, so you should change a little bit. So from reference destinator in site A. So basically site A is like from the bottom part. Okay. So site A basically is the input. We're going to change it to out to connector, and then reference destination out, which is out to the DIMM card. Okay, from the connector, it goes out to the DIMM card. Remember our DIMM card is J1, all right? So we specify J1, and then the channel ID for this component will be 0. Okay, and then you can click on next. And then you can see that there is a whole list of signal assignments that we need to assign. Okay, we need to define what is the signal type and so on. Okay, so all this we have already done it for you, don't have to worry. But if you bring in your own connector model, you might need to manually set this up based on your understanding of your board design. Okay, but what we can do is to update signal properties from a CSV file. This already have all the pre-configured signal type, signal index configuration. Okay, so if you follow me, you can update signal properties from a CSV configuration file, and then you can update the connector ports and open. Okay, so you can see everything is defined properly. Something went missing. Let me see. Sorry, give me a moment. Let me just check. certain things. It's a bit strange. Ah, it's missing the reference designator. Okay. Yeah, something went missing. But I think to save time, yeah, by right, in the Excel spreadsheet file, you should also have the reference designator being labeled, but I think it seems to be removed. All right, so I will just go to the slide. You can just observe the slide. Basically once we update the CSV file, it should have this input F1 and so on, everything already defined properly for you. Okay, so I think the CSV file it was not updated properly, so things are missing, so we can skip that step. But basically, once we have the connector being set up, that's where we can include the bus wire, which we have tried it earlier on. Okay, and then that's where we connect the memory controller. Um, yeah, I'll just briefly run through since this schematic might have issues. Uh, Basically, we add in the controller, which is acting as a CPU. All right, so this is the controller before going through the breakout VRs and so on, right? So this will be the CPU. Again, how I define it based on the pre-layout, all right, the reference designator. Since this controller will be connected to the pre-layout, all right? So when we set up this controller, we take the reference designator from the pre-layout so that the controller is able to connect to the pre-layout. Okay, the pre-layout may contains with the breakout traces and so on. Okay, note that uh, for this memory design, we do support simulating with IBIS file. If you do not have the IBIS file, no problem. We have generic transmitter that you can use as well. Okay, so that's the setup. And then, we enable the controller, right, in VR, and then we set up what we want to simulate over here. Okay, so in this case, we're simulating DQ0 to DQ7. Okay, um, so that's the setup, and then we can create a group to actually characterize all traces. You can take a look over here, DQ0 to DQ7, we create a group. And since all DQs will have the same electrical properties, we just group it up so that we just have to modify it one time. Okay, so we can just change it to 30 ohms. That's the termination for the memory. All right. And then, yeah, I'm so sorry that this schematic is not being updated. If you try on yourself, you realize that when you try to connect the wire, it doesn't hook up to the edge of the component. So therefore, there's some issues with this schematic. But generally, once we hook it up with the CPU model together with the breakout vias, breakout tracers, together with the S parameter connectors and the DIMM card, all right, DIMM card, and eventually to the DRAM. If we simulate it with our memory probe, this would be the results that we get from our eye diagram. Okay. So apologize for that schematic might not be able to work. You can refer to this slide to just understand the flow and what kind of analysis you can get. I just want to touch on one point, which is on the memory probe, which I forgot to highlight. Yeah, so this is the memory probe, which is from the memory designer side. If you double click on the memory probe, you should be able to see similar things from what you see earlier on with the SEDES eye diagram. So this memory probe is quite comprehensive. It allows you to define some of the voltage settings for the different signals, like for DQ, your control signals, your clock signals. I think you are able to insert iMask as well. Okay, so iMask for your simulation. And from there, you are able to set up what are the signals you want to analyze, right? So in this case, I want to analyze the RX output of my DRAM, all right, which is my receiver from DQ0 to DQ7. So this is something I've set it up, okay? And then the measurement is similar to what you see in iProbe, looking at the eye width, the mask margin, and so on. Okay. So these are some of the things you can work with your memory probe to actually do some measurement over here. Just to add on, we have this design exploration. basically this design exploration allows you to specify the specifications, your own personal specification. It could be stricter than the industry's compliance. All right. So you can, for example, for the eye height, let me just quickly do that. Okay, so if I add the eye height, you can see that I can specify my own eye height and eye width value. All right, so this is something that you can work with if you plan to have a stricter requirement as compared to the compliance. All right, and then this on design exploration, your own custom requirement. But of course, if you want to ensure that you comply with the industry standards, then for ADS we do work with together with our Infinium compliance app. So Infinium is coming from our Keysight hardware as well. So it's the same test platform as ADS, and then we are able to run the compliance tests in the simulation world as well. Right. So this is something that we are able to do in our simulation side. Okay, so I apologize that this schematic, there are some issues. Again, if you try to, connect the wire, you realize that you can't snap it to the edge of the component. So therefore, yeah, I think this part maybe I will complete the schematic and send it to everyone over here after this workshop session. Okay. Okay, so yeah, just to show you, if we just compare the results, right? Just simulating the dim cut, all right. You can see that the eye, is much open. You don't see much of the crosstalk, right? Remember how we identify crosstalk? You can see that over here there are some crosstalk coming in over here. Okay, so at least for the dim cut, the crosstalk is not severe. But for this schematic, when we start to include more and more things like the breakout traces, the breakout vias, the connectors, you can see that for this trace here, you can see that a lot of crosstalk effect is coming in. Okay, so yeah, hopefully what we have discussed earlier, you look at this plot, you're able to identify that there's actually some crosstalk issue coming from this eye diagram, right? But as long as I would say if the eye still meets the eye mask requirement, um, it's still relatively safe. Yeah, I would say. But do check again with the standards. There could be some crosstalk, how do I say, crosstalk limits that you might need to comply with. So always cross-check with the compliance details, leverage on our Keysight compliance test, which can just immediately tell you all the reports on, whether your design does it pass or fail the compliance. Okay. Let me see if I have some of the compliance report here. Let me just quickly take a look. Yeah. So just to share as well, this is one of the compliance report that is simulated using our memory designer. So this is the same as our Infinium compliance test. All right. If some of you are familiar with our Keysight Infinium scope, the Keysight Infinium scope does have some compliance tests, and this is the same test that is being used for inside the ADS simulation. Right, so from this compliance test, it will generate a report to tell whether is it pass or fail, and then it will check all the different standards, and you're able to look at the report. I think there's some snapshot, maybe yeah, screenshot mode off, but you can look at the different tests, look at whether does it meets the requirement or not. All right. So this report is not in your slides material, but if you're interested to take a look on your laptop, you can always go back to ADS main window, okay, and then right click, there is a Explore in File System. So Explore in File System, under the data folder, all right, if you scroll all the way slightly down, you should see a PDF report. So if you double click on this PDF report, this is the compliance test report that is generated from ADS together with the Infinium compliance test. Okay, so just take note, we have compliance test that works that works the same as our Keysight Infinium oscilloscope, Infinium scope as well. Okay. Okay, so any question? I think this is the last part for part two. So I think we briefly take a look at how we can run memory design simulation. Of course, there's much more we can work with. We can work with dual rank. Um, when it comes to DDR, there's dual rank and so on. So we managed to look at how we can include a S parameter file from a connector from Molex and include it in our simulation and run and look at this kind of eye diagram, right? And then for compliance tests, as mentioned, Keysight Scopes has the best simulation to measurement integration. So we do have our Keysight Infinium test app that can run together with our ADS software. Okay. I just wanted to highlight one last thing before I think we go for a break. Um, So for this memory designer, we talk about DDR4, but just take note there are many, many other standards that our memory designer is able to support, right? So such as from DDR4, DDR5, LPDDR4, HBM3 if you're working on those technology. So a wide range of technology that memory designer is able to support. Okay. With that, any questions on memory designer? Hopefully you can see that for memory design, where it involves a lot of DQs, a lot of control address nets. Memory designer, is able to simplify all this by smart component, just a single bus for you to represent all the traces and helps you to be efficient when it comes to memory design work. Okay. Any questions? Yeah. So far, okay. Okay. If not, I think we can take a 10 minutes break, and then we'll move on to the last part on power integrity. Okay, so I think everybody is back. All good to go. So the last part will be on power integrity. Okay. So we will be looking at this slide deck, which is on PI Pro and SI Pro workshop. Okay, so you can refer to this workshop. Okay, so for this workshop, it will consist of both the SI Pro and PI Pro. I won't go through the SI Pro again because it's pretty much the same as what we have gone through earlier for the HDMI. In fact, it's a little bit less detailed, all right? So for this first three labs, you can take a look for sure, but we will skip it for this session over here. All right, so this part is on the USB. All right, so if you're interested to look at USB, you can always feel free to refer to this slide and kind of understand, a little bit more about USB simulation, but the workflow is about the same. I think one of the common questions I oftenly get from customers is about SI Pro's accuracy. Okay, so if you are interested to look at a case study on SI Pro's accuracy with measurement. This is one use case that we can share. All right. So for this is on the Xilinx board, which is on 28 layers stack up. Okay, and the measurement was provided by Giga Test Labs. All right, this is like page number 10. So if you look at page number 11, it shows you the simulation that was being used. All right, and then how does it compare between simulation and measurement results over here. So this is one of the test case that we are able to correlate well. So you can just take a look on it because this is one of the common questions I got from customers. All right, and then I think this part, I think you have already experienced it. All right, what is the workflow, from late import, and then we start to do the EM simulation, and then we bring it back to schematic, and then we do all the simulation setup to look at the eye diagram analysis. Okay, so this is what we have gone through. Okay. So for this part, we'll be looking at a Texas Instruments board. Okay, we call it the Panda board. Um, so this is the board layout with together of all the components, right? So it's on the system on chip component over here. So we're going to simulate that. Some of the high-speed digital interfaces that is on the board, right, is being specified over here. So you can take a look. The Panda board layers stack up, total of 8 layers, 4 signal planes, 1 power plane, 1 ground plane. All right, so quite a less complicated board, I would say. Okay, so this is the board. So for this board, it does use Allegro for import. So I don't think. Let me just take a look. Let me see. Yeah, so there is a .brd file that you can import. Um, but usually to import Allegro files, you need to also install the one of the PCB Cadence, PCB Allegro software. Yeah, that is one of the requirements. But not to worry because we already extracted the board out for you. We can straight away start with the workspace. All right, so I will show you how to launch the workspace later. We'll just focus on this slide deck for now. But basically, if you have any Allegro files that you want to do the import, you can always refer back to these notes, right? Go to File, Import, Cadence Allegro, and it should have the status. Just take note, you need to have the PCB Allegro. Not sure if I have it here. Yeah, something like this, PCB editor, viewer, the Allegro software installed, right? Then when you do the import, you will leverage on a feature in Allegro called the extractor software that will help to extract the PCB board and then upload it into ADS. Okay, so that's the requirement if you are importing any Allegro files into ADS. Okay, so yeah, I think let's straight away take a look at our workspace. Okay, so let's go to ADS main window. Okay, so if you are still at the previous workspace, we can actually close the workspace. Okay, we can close the workspace. And if you want to save it, you can save it. If not, you can just close it. I'm going to save it. Okay, and then in the meantime, you should receive a zip file from us. Let me just go back a little bit. Uh, yes. Right, so you should receive this zip file. If it's not unzipped yet, I would recommend to unzip it. I would suggest to unzip it in a location, uh, extract all. Yeah, I would suggest to extract it to the document folder. Okay. Um, yeah, somewhere whereby the system path is short. Okay. So in my case, I'm just going to extract all if it's not extracted, and I'm going to browse it to documents and save the extracted files into the document. Okay, so just make sure the files has been extracted out and saved into your PC. Okay, I will pause for a while to check, make sure everybody does that. Yeah. Okay, any issues, do let us know. I can repeat the steps again. If you can't locate the file, let us know. So yeah, again, just make sure to extract. If it's still under zip file, just make sure to extract. Extract. Yeah, I think I've already extracted it. Extract to a path that is shorter, so you can look at documents. And then once it's extracted, you should be able to see the file being extracted out, and you should be able to see these 3 folders over here. Okay. Okay. Any issues, let us know. I'll just pause for a while before I move on. Make sure everybody's okay. So yeah, once you have extracted it, let's go back to ADS, and then we're going to go to File, Open, and Workspace. So when you go to File, Open, Workspace, go to the directory whereby you extract the folder earlier. Okay, so I'm just going to go to Documents and locate my SI Pro folder, SI Pro student. Okay, so we can click on, let's do reference. Okay, in case you're stuck, the solutions are inside reference, so you can take a look. Okay, so click on reference. If you see a warning message, just press no. Okay, and then this will be the workspace that you will see. Okay, so inside this workspace, we'll have pretty much all the solutions except for thermal and electrothermal. Thermal and electrothermal, I'll run through step by step with you. Okay, but yeah, this would be it will contain most of the solutions for this workshop material over here. Okay, so let us know if you are unable to open this reference workspace. All right, and then we will help you on that. Okay, I think so far all good. Everybody looking at the screen. Okay. So moving back to the slides, as mentioned, I will skip all the SI part. The flow is pretty much the same as HDMI, mainly just to locate the signal nets for the USB. And then once you locate it, create a SI analysis, do a drag and drop, and then create ports. I think all this you have gone through, so I won't go through that again. Set up the frequencies and then run the simulation. Once you have run the simulation, you can plot the S parameter results. You can plot the TDR, which I've gone through already. Yeah, so a little bit explanation of what is being simulated and so on. All right, and then how do you characterize high-speed channels? Yeah, look, connecting basically is bringing the sub-circuit. Or remember, we generated sub-circuit from SI Pro, and then we feed it into our channel simulator. Okay, which is something like this. All right, if you remember, we feed it into our channel simulator. We are now at slide number 45. I'm going a little bit fast because all this we have already run through previously. Okay, so yeah, we have then connected up into the channel, and then we can plot the eye diagram results earlier. So all this we have stepped through earlier is pretty much the same flow for USB as well. Okay, so we're going to start with power integrity. So power integrity is all about power, I would say. But I think the main thing is about power distribution network. This is a key term that is often used by power engineers or PI engineers. So the roles of the PDN is to really make sure that the power supply from from the chip, to another of the component. The goal is to at least maintain a constant supply voltage. All right, we don't want to have any voltage drops. Likewise, because of the high switching current that will be propagating through the PDN power nets, we also doesn't want the power nets to have a lot of how do I say, the resonance, because all these resonance will start to create spikes, voltage spikes to your power signals, and then it might eventually cause issues like EMI and so on. Right, so these are some of the things that PI engineers look at, looking at DC-IR drop, how much voltage drops, from the VRM all the way to the dynamic sync, and also, any possible, or rather the PDN impedance. That's also one thing that PI engineers always look at to make sure that their power nets meet certain PDN target impedance. And then, of course, any possible resonance, they want to minimize it so that this can avoid any potential of the EMI issues over here. Okay, so that's generally the idea of PDN. There, you can see over here, as the PDN is often large conductive structures and carries the high current or high switching current, it usually has potential to cause significant radiated emissions. All right, so PI is all about how we can mitigate it and so on. Right, so we are looking at slide number 51, which gives a little bit more detail about what is DC IR drop, and usually for at least for ADS workflow or design flow, when we are looking into power integrity professional PI Pro solution, we always advise users to start with DC IR drop analysis first, because DC IR drop is a quick good check to make sure that your VRM, your voltage regulator module or modulator, is well connected to the sink before you move on to other analysis such as your AC analysis or even your power plane resonance. So always start with DCIR drop. And what is DCIR drop? Basically is to compute basically a simulator will compute voltage, the voltage drop, current, power loss density, right? There's across your power nets. And then really checking and make sure that the voltage that is present across the ICs or your sinks in this case is still at the voltage level that is required. And at the same time, yeah, so again, due to excessive voltage drop, right? Because when the power voltage propagates through the PCB board, there's some resistance that will cause some voltage drop over here. Okay, so the power supply voltage at the IC might fall below the recommended minimum voltage. All right, so that's the purpose of DCI drop, to make sure that it doesn't fall below the recommended minimum voltage. We also want to check and make sure that there isn't any excessive current densities across the power rails, because this will generate excessive heat, leading to board failures and so on. All right, and also any excessive current in the stitching vias can lead to via failures, losing connection. So these are some of the things that you might want to take note when running through the DCI analysis, right? So you can look at one example over here. From the VRM, it's actually generating 1.2 volts, but after propagating the power rail or going through the power rail, the voltage is going to drop. And we just want to make sure that this voltage here is still sufficient to drive this IC over here to operate. Okay, so we're going to look at how to analyze a DCI drop. Okay, so I think this is a Xilinx PDM. All right. So this is just a example use case. We are not going to look at this board, but you can see from the simulation setup here, the VRM is coming from this component U4, all right, 1.2 volts. But as this voltage propagates through the power rail, you can see that the voltage drops to different levels at the sink. And the thing is, we want to make sure it pass. All right, so you can see there's a whole list of tables here to show you that the voltage presence at the ICs are still meeting the recommended minimum voltage over here. Okay, so yeah, for PI Pro, we are able to look at this kind of color plots for you to sort of identify how much of the voltage is being present across the power rail. We can also look at power dissipation and current density visualization, okay, across the board over here. Okay, so we're going to start working with the Panda board, and we're going to look at how to set up the DCIR drop analysis in PI Pro. Okay, so we are going to look at, just to highlight a little bit. So if we look at the Panda board, all right, at slide number 55, it should show you both the layout of the VBAT, right? So VBAT is one of the power rail that we're looking at, and the VBAT will be connected to some of the components like the audio chip, the Ethernet, HDMI, Bluetooth module, and so on. Okay, and if you're interested to look at the schematic, we have it at the top right-hand corner, that shows the schematic of how the connections from the VRM all the way to the different ICs over here. Okay, so you can take a look over that. So for the VRM, it's going to supply 3.5 volts. This is provided by the vendors, and how much of the current consumptions by each of the ICs. They are all listed here, and usually they are provided by the vendors as well. So if you are able to get information of the current consumption by each ICs, you should be able to define them in the simulators and look at DCR drop performance. All right. So this is the design that we'll be looking at. All right, looking at DCR drop simulation. Okay, so we're looking at slide number 56. So I'll go back to ADS now. Okay, so just make sure everybody is at the reference slide Panda board. Okay, and we are going to look at slide number 56. All right, so if you look at this Panda board over here, you can look at my screen first. All right, if I double click on the layout, all right, so this is the layout from the Panda board, right, from TI, Texas Instrument. All right. So same thing, you can do the import using .brd file, and then once you have done the import, you can check on the substrate, right? The substrate, maybe I forgot to mention, the substrate is at the substrate editor. If you see a rainbow box here, that's the substrate editor. You can click on it and it will show you this simple 8-layer board over here. Okay, so that's on the imported board. And then, yeah, I think this is where you can start to launch PI Pro or SI Pro, PI Pro. Okay, let's use PI Pro now. So under the Panda board, you will see a VBAT. So you can double click on the VBAT. Okay, so that will launch the Panda board into PI Pro. Okay, so just to highlight again, SI Pro, PI Pro, they are on the same UI, I would say. All right. But since we are now talking about power integrity, I will just use PI Pro. Okay. Okay. So just make sure everybody launch it. All right. So this is the Panda board. Again, use your left mouse to click and rotate. It should give you a 3D view. All right. And then we are going to look at slide number 56. Okay, whereby we're going to add in our VRM. All right, so you can see from slide number page 56, we're going to add in a DC analysis. All right, so you can right click on analysis and you can add in the PI DC analysis over here. Okay, once you have added PI DC analysis, you can feel free to rename it, no problem. I'm going to rename it as well, DCIR drop. And then we're going to add the VRM. All right, so how do we add the VRM? Okay, based on the lab seems to be the last part. We will add the ICs first, which is the dynamic sync. Okay, we call it the sync. Basically, it's the ICs over here. If I go back to the slides, okay, we're going to add the ICs from the OMAP, USB, Ethernet hub, HDMI, all right? All this will consume current. So we're going to add this in. So if you look at slide number 57, yeah, 57 will guide you, 57 all the way to 59, they will guide you on what are the key components you need to add into your sync. Okay, so I'm just going to search for my U11. Okay, so yeah, I search my U11 and I'm going to drag and drop it to my sync. Okay, and then when you drag and drop it to the sync, it will actually ask you, which of the power rails that you would want to simulate. So as mentioned earlier, we're looking at the VBAT power rail. All right, so if you select VBAT, okay, you can see at the background, it's a bit hard to see now, but the VBAT power rail is being highlighted for you. Okay, so you can click on VBAT and click OK, and this will add the VBAT trace for you. Okay, let me just hide things a little bit. If you're curious how VBAT is over here. Okay, if you want to play, you can click on conductors hide. This will hide all the PCB board for you. Okay, and then you might see some components still lying around. You can check off this C, click on C, and then this will be the power nets, power rail for you. Okay, so these are some tricks that you can leverage on. Okay, so we have already added one sync U11, and if you look at slide number 58, we're going to define the current consumption by this IC over here. So you can double click. It looks a bit different. Let me see. Yeah, we can set to 3 ampere, and then the voltage tolerance is 5%. So it's a bit different. I think we did some updates. And then we're going to choose the equal voltage for all the pin current model. Okay, so we can leave it as default. If you have package model for the ICs, do feel free to add it in. Okay, but in this case, we don't have the package model, so I think we can just leave it as none. Okay, sorry, the DC current should be 1.6 ampere. Okay, so sorry about that. For U11, do change the DC current to 1.6 ampere. Okay, I'll pause for a while. Okay, we're at page number 58 if you are looking at the slides. Okay, so once done, we can start to add in all the other sinks. All right, if you look at slide number 59, we're gonna add in U9, U5, U3, U21. Okay, so the same thing if you remember to apply and done. Okay, once you're done, click done. All right, so if you look at page number 59, all right, page number 59 is over here. Okay, it will indicate to you what are the rest of the sync that you need to include. U9, U5, U3, U21. All right. Are you able to find slide number 59? Okay. All right. So if you look at this window here, you can see U9, U5. All right. So do add it in. I will show you also. Okay. Under the component. Okay. Search for U9. And I will do a drag and drop as well. Okay. To the sync. And then I think it'll keep popping out for you to select VBAT. So just make sure to select VBAT. Okay, and then the same for U5. Add to the sync, select VBAT. U3, VBAT, and then U21. Okay, click on this component and drag it to the sync, and then select VBAT. Okay, I'll pause for a while before I move on to the next step. Okay, so just make sure you have all 5 of the sync. Okay, that is connected to VBAT all added together. Okay, so this is the ICs for the for the HDMI, for the Internet hub, for the cameras. Yeah, so we all include them into the power rail. Okay, so I'll pause for a while. Okay, yeah, so that's on adding on the dynamic sync. So the next step is we're going to define the current consumption by the ICs, right? So what you can do is you can right click under sync and select all properties. Okay, once you have select all properties, you can start to define the current, right? For example, if you look at the same slide, same page number 59, right? You can define 0.4 ampere for U9. Okay, so I'm going to do that the same. Okay, so I'll leave it here. All right, so just make sure you manage to configure the current to be the same as well. Okay, so once done, you can click done. All right, and we are done setting up with the sync. Okay, so the next part is we're going to add the VRM. Okay, so just to share, I think one common question I received was, if you look at the slide here, the VRM, it seems to be coming from a resistor, right? Why do we add the resistor as the VRM? It's a bit strange, right? So let me explain a little bit. Just remember we are looking at R186, okay? And if we scroll back to the schematic, okay, of my schematic here, okay, you can see that VBAT, there's this switch VBAT, there's an inductor and a capacitor, VBAT out with a receiver, with a resistor, and then towards VBAT. Okay, so basically, initially from the output of this IC here, we do get a switching voltage. Okay, but once it goes through the inductor and the capacitor, we will get a DC voltage over here. All right, so therefore, for at least for this DCI drop, we are modeling a constant DC, at least for this case here. So therefore, we just specify the DC output to be coming out from R186. That's the reason. Okay, but of course, if you want to model the switching voltage, that is possible. I will show you later on. Let's just add this R186 as the VRM for now. Okay, so that's the reason why we add the R186. Okay, so over here, we are looking at slide page number 60. We're going to add the R186 component. We're going to drag and drop and add it to the VRM. Okay, so I'll do that. R186. Okay, make sure you're able to search and then drag it to the VRM. Okay, and then you'll be asked to select VBAT again. All right, so you can click OK. So there are some warning message. We're going to resolve that. Okay, so just to explain, if I double click, you can see that now we are looking at package VRM, right? So the package means the output is DC, okay? That's the simple example. But if you are looking at switching voltage, if you want to model that, that is possible. We have like discrete buck VRM, which is directly taken from the output of the inductor, all right? Meaning that if you want to model the switching characteristics of the voltage, means that you would, specify the different pins. I think this is something a little bit more advanced already. But just to share, I think it's a common question I receive, meaning that I'm getting the output from the inductor, this part. Okay, so depending on the model that you are modeling for your VRM, if it's a discrete buck power or discrete buck VRM, then the output is coming from the inductor. Then you need to specify the positive, the negative pin from this component onwards. But since we are just using a very simple package VRM model, we just want to get the constant DC. That's why we choose the resistor. Okay. So let me just go back a little bit. Okay, so if you look at page number 61, before we even define what kind of model that we need, you can see that the warning message says that there's no pins connected to the minus terminal. Okay, so you can see that it's missing over here. Okay, so let me just turn on everything a little bit. All right, so if we look at where the R186 is, all right, and then if we look at where is the nearest ground, all right, remember from the inductor down to the resistor, all right, then there's a shunt capacitor. So this is the nearest ground that we can take from the minus pin as a reference, okay, as a reference. So if you look at slide number 61, we're going to search for the capacitor C237. All right, and then we are going to include the digital ground as the minus pin. Okay, so I repeat again, search for C237. Okay, and then when you manage to find C237, expand the component, and there is a ground pin, right? Digital ground. Click it and drag it to VBAT R186. All right, and then this will actually remove the warning message over here. Okay. So this capacitor ground is the nearest ground pin that is nearest to the resistor. So we use it as a reference for now. Okay. Yeah, so moving on to the next page, that's where we define the VRM output voltage. All right, so in this case, you can double click on the VBAT R186 and we can specify 3.5 volts. And then of course, some design, there are sense lines. Sense lines sometimes help to boost to boost voltage, right, to reduce the amount of DCIR drop. So if your design has sense line, we can also support, defining the sense line. You have to define the ports, where the ports for the sense lines is. Okay. So yeah, once you have defined 3.5 volts, you can click done, and that will be okay. And then we can start to run the simulation. Okay, so there are no other components included in series. Mainly it's just taking the ports, all right, and then just excite the voltage over here. Okay, so we are done. We can just double click on run. The simulation might take 1 minute. But just to take note, for PI Pro, generally it uses the FEM engine, all right, to solve most of the simulation problems. Okay. All right, so my simulation is completed. And then if yours is completed as well, you can click on the results part. All right, and then you can double click on overview. Okay, and then it will give you a power graph plot. All right, to show you that from the VRM, all right, as the voltage propagate across VBAT, how much voltage is being present across your ICs, and does it still meets the minimum voltage condition, right, for your IC side.
Excuse me, what do you mean? What do you mean by sense line? I think you mentioned about sense line.
Yeah, sense line is just additional line that is, I think, connecting from the VRM to other parts of the either ICs or the power rail. It's sort of like a booster voltage to boost a little bit of voltage to make sure that the voltage at the ICs doesn't drop too much and doesn't meet the minimum condition. Yeah. So some designs does have sense line from what I see. Yeah. Okay. So this will be the power graph. Useful to know all the voltage condition. Does it pass or fail? All right. And then you can look at some of the, how much of the DCIR drop, from the VRM to the ICs, and so on. All right. So all the different parameters. VRs as well, does it meet some of the overheating, temperature and so on. We'll look at thermal more, but at least for the DCI drop, we're able to look at some of the VRs condition. Okay, so different information, you can look into that, and so on. Okay, so power graph is one of the tools results that you can look at. Some designers also look at the voltage, so you can double click on voltage, and yeah, this is just on. Let me just hide everything.
Could you return to the previous two slide? I think I saw a thickness. Is that it? The 30 micron or something like that. 30 micron. Yes. Plating.
Mm-hmm.
Is that the thickness of the copper?
Let me see.
Because radius is the radius of, is that a pad?
The radius will be the radius of the vias. The
Yeah.
plating.
I think the thickness. Okay, the thickness of the plating of the via.
Yeah,
The
correct.
plating for the via surface.
Yeah, I think the plating will be the thickness of it. I will check again, double confirm. But the radius will be the VR radius. And
Because
then how
I
much?
think the purpose of this is to calculate the current density. Is this correct?
Correct.
Yeah, area. Yeah, area, and then maybe you can calculate current density.
Correct. So there's a current on this column to check whether does it meet your, sometimes PI designers will have a certain maximum current that they want to at least have some standards, yeah, to comply with for the VR current. So I think they set some maximum current, and then just to check everything is just below the maximum current, because we don't want overheating and so on. Yeah, that's one way to check. Yeah. So you can see any violating current. So I think there are two VRs that have too large of a current. Maybe that's something you want to fix and so on. Yeah.
Okay.
Okay. Yeah. So coming back, you can double click and look at the voltage plot. These are some just fanciful images to give you a little bit more insights, how the voltage drop across the VBAT. All right, the further east, then there's more DCI drop. You can look at current density as well. And then you can also look at power loss density. Yeah, you can look at the power loss density, how much of a power loss there's across the VBAT power trace. Yeah, so these are some of the things you can look at for the DCIR drop. So we are done with DCIR drop. The next part is on, yeah, so I think the slides go through a little bit, what are some of the images or results you can look at, look at voltage drop, current densities, and so on. So a few results that give you a little bit more insights on your power rail. The next part is on PDN impedance. This part is also important because I think out in the industry, a lot of the PI engineers always talk about target impedance. All right, target impedance. They need to make sure that the power rail that they design meets the target impedance that they want to design. So oftenly you hear target impedance across the PI engineers over here. And why do we need PDN analysis? All right. So basically, it's mainly to ensure that your PDN provides a low impedance path for the voltage regulator to the ICs. All right. Um, so basically, any excessive impedance can actually generate excessive voltage noise, also called dynamic. This is dynamic IR drop, whereby the IC power supplies draw large amount of transient current. All right. And I think also it's also good to run AC to ensure that there is not much of a resonance. So I think we have another simulator called the power plane resonance. It's really finding resonance coming out from your power rail, because all these resonance may potentially create the EMI issues over here. All right. So PDN impedance also another important analysis to work with, and a lot of times, PI engineers will have a target impedance to work with. Okay, so I think this slide number 70 talks a little bit on how to actually determine the target impedance, which is a little bit difficult. So how you can basically this is the equations to sort of determine what is your target impedance. All right, how much of a ripple percentage, VDD, power max, and so on. So it's a little bit tough. I'm not sure if this slide talks a little bit more. I think it does. You can take a look a little bit more theory on that, and then all the different conditions that affect the impedance on that as well. All right. So you can take a look at slide number 70 and also 71, which talks about the different factors that will affect impedance in general. Okay, so you have the series inductance, you have the package barrier, you have on-die capacitance, and so on. All right, so high frequencies, the on-die capacitance will provide the low impedance and so on. Right, so all this will happen. And then how, when you talk about impedance or PDN impedance, a lot of times we talk about decoupling capacitors. The decoupling capacitors will sort of affect how your impedance profile changes as well. All right. So basically the decoupling capacitor is also something that we will include into our PDN impedance analysis and to see how we can actually improve the target impedance and so on. All right. So I think the capacitors have different parameters like ESR, ESL, SF, SRF. All this will affect the impedance profile of your power rail. All right, so again, this time around, we are using EM simulation again, and PI Pro uses the FEM engine, basically to calculate your PDN impedance. All right, so definitely you need 3D simulator because with the 3D EM simulators, any of the current distributions will be considered, all right, and so on. So current distributions overlap, spreading of inductance become a complicated function of the location of the capacitors, and so on. So the only accurate way of estimating impedance profile is with a 3D impedance. Okay, so that's one thing about PDN impedance. So we are going to look at the same VBAT. We're going to learn on how to actually set up the PDN impedance in PI Pro. How do we plot the impedance profile? How do we work with vendor components? I think there's one part that talks about how do we do decoupling capacitors optimization, decap optimizer. The decap optimizer is to mainly optimize the BOM list of the capacitor while maintaining the impedance to be below your target impedance. Okay, so we're going to look into that. Again, we're going to look at the same VBAT power rail, which is over here. Okay, and then we're going to start looking at page number 77. Okay, so page number 77 will show you on how to actually set up the PDN impedance analysis. Okay, so we're going to go back to PI Pro. Okay, and then we're going to right click and start to create a PI AC analysis over here. Okay, so the solution is already here, AC analysis, but we'll just go through the lab. All right. So again, I can rename it as PDN impedance, for example. Okay. So once you have right click, created a AC analysis for your PDN impedance, what you can do is, oh, sorry, make a mistake. Let's just delete that. I just remember. Let's just delete that. Because we have already set up the VBAT in our DC analysis, we can just duplicate our DC analysis to the AC analysis. This is a much quicker way. Okay. So right click at your DC IR drop analysis earlier, and then to copy and then PI AC analysis. Okay. And then you can start to rename it as PDN impedance. All right. So all the VRM or the sync that was previously defined in your DCIR drop, it will all be copied to the AC analysis, which we'll be using it for our PDN impedance. Okay, so just make sure to duplicate it to the AC analysis. And once that's done, all right, as mentioned earlier, for PDN impedance, we will need to include the decoupling capacitors. All right, so how do we identify decoupling capacitors that is across our VBAT here? And so usually decoupling capacitors, they are connected between the power rail and the ground plane. All right, so what we can do is we can actually highlight both the VBAT and the digital ground. All right, and then what we can do is we right click and select instances that is connected exclusively to the selected nets. All right, so we're going to only select those components that is connected between the VBAT and the ground itself, all right, which is the decoupling capacitor. So you can just select that. Oops. I think one thing you might want to take note is might want to cancel off this C237. That's something I would do. Okay, and then I will do it again. Okay, just to make sure. Okay, so it highlights all the capacitors. You can see on my layout, all these circle dots. These are all my decoupling capacitors that are connected exclusively between VBAT and the digital ground. Okay, so what I need to do is I just have to select one of the decoupling capacitors. All right, you can see that as I click and drag, it selects all the decoupling capacitors. What I need to do is I just need to drop it and it will add everything for me. Okay. So there are a lot of warning message. I think by now you should know that we have the auto assign model. that can helps to quickly assign the capacitor model. So let's give it a try. Hopefully all works. Okay, so I think it's now auto assigning. It takes time. Okay, maybe not all it will assign. Like all this, I don't think it's able to identify the component. All right, so for all those that are still having warning message, you might need to manually add it as a lump component. All right, so let me just take a look. 268, this is on 4.7 microfarad. Okay, so this is on page number 80. Okay, on the decoupling capacitor, basically page number 79 and page number 80 will show you on the steps on how you can actually quickly identify decoupling capacitors that is connected between these two traces. Okay, so you can click done. And then I'm going to add a few of it. 271 picofarad. Okay, so I will pause for a while. Make sure everybody can follow. Okay, apply and that. Okay, so once you have followed page 80, I think all the warning message should be done. All right, so I'll just pause for a while to make sure everybody can follow. Okay. Yeah, so I think I'll pause for a while. I can see some of you still working on it. Okay, so I think for those of you who are done, or rather if you find yourself you can't, or rather, basically we have a solution already done for you. Okay, so you can, to save time, you can always go to AC analysis. That is the complete solution that we have already loaded for you in PI Pro. Okay, so yeah, if you want to skip those steps of manually adding, you can look at the AC analysis. Okay, and then from the AC analysis, you can double click on options. This is where we specify the frequencies that we want to simulate. Okay, so it depends on your application. Yeah, the simulation frequencies depends on, yeah, your applications as well. Okay. I will check on PIAC. But yeah, typically we do see simulating, up to 300 megahertz. It doesn't go up to gigahertz. Usually for power integrity, the highest I've ever seen is about maybe 500 megahertz. Yeah, it's all in the megahertz range. So it depends on your application, how high you want to analyze, but usually it is across the megahertz range. Okay. Um, so take note, we also save some field storage. This is for the current density plots we will show you later on. And then some of the default settings, we can leave it as it is. And then once that's done, you don't have to run the simulation because I think we have already done it. Oh, sorry, you need to run the simulation. All right, so I'll run the simulation. Okay. While running the simulation, I think we can just take a look at the slides. So just double click on run for the AC analysis. So I think the simulation might take 10 minutes or so. Uh, so we'll just let it run behind the scenes. But yeah, basically towards the end of the results, what you would see is that we can actually plot the PDN impedance. All right. And when you look at the PDN impedance, you can see the impedance profile of the power rail towards the different ICs. Okay, so this is one results you can look at. And then over here is that for PI Pro, we make it easy for you to kind of adjust the decoupling capacitors and see how it affect the impedance. All right, so if you look at slide number page 84, we're just going to focus the PDN impedance for U9. Right, so U9 is
Smith,
having this profile.
why the shape of the curve is like that? So the importance magnitude goes down and then goes up again.
Because of the power rail, of the dimension, it might affect the impedance. And of course, any decoupling capacitors, decoupling capacitors will affect the impedance profile. So sometimes it will have this kind of characteristics, and usually we look into the log scale for the PDN impedance. Yeah, so it could be coming from the power rail traces that affect the impedance, and of course the decoupling capacitors. Yeah, so if I
The
take a look,
typical shape, is that the typical shape of the PDN? Like
yeah,
U, V.
yeah. So for
Yeah.
example, for this case, yeah, you can see, yeah, like the shape of this VBAT, right? Some of the trace width is very narrow, so maybe
Mhm.
you have higher impedance, but some
Yeah.
part is wider, right? So you have lower
Okay.
impedance. And then of course your decoupling capacitors, because decoupling capacitors will affect the impedance profile, and it will help you also to make sure your impedance profile is below the target impedance. Yeah. So these are the main two factors I say that affects the impedance profile of your power rail. So coming back, yeah, just looking at U9, right? U9 have this profile. What you can do is, for example, if you go back into one of the components and just change it, from 44.7 to 1 microfarad, all right? You don't have to simulate. No need to re-simulate. When you make that changes to the decoupling capacitors, basically, the profile will change. Okay, I think it's not shown here. Once the simulation result is done, I will show you, but basically you don't have to re-simulate. You can disable decoupling capacitors, the profile will change immediately, and this is something that is useful for designers because they want to know, is it necessary to place a decoupling capacitor there during their design? Or should they change to a better or another value of decoupling capacitors? This is, I call it the design exploration, where they tweak different values and see how it impacts the design or the impedance. And then from then, the designers can make an informed decision what component they should change to, or should they even place it there. Um, so that's one on, changing the capacitor value. We recently also added virtual component model, whereby you can place, let's say this is the board, the first prototype board. Apparently, the PDN fails, right? So you want to add virtual component to see whether you can place capacitor at certain location. Does it help to improve the PDN profile? So we have added this virtual component model, which is also helping designers for any design exploration stage. Okay, so this is our virtual component model. Let me just close all the power graph. Okay, yeah, so the simulation is done. Let me just show you. You can just look on my side if your simulation is not done. All right, so I can plot the PDN, all right, and then, different um, path towards different ICs will have different impedance profile, right? So just to show you, if, for example, today I decided not to use any of the decoupling capacitor, I'm going to disable all right? You can see that all the profile changes, all right? And, if I don't use decoupling capacitors, this might fail the target impedance, right? It's very high, right, for power rail. So, that's the purpose of adding decoupling capacitor to bring everything down. Yeah, so that it meets the target impedance over here. Okay.
Mhm.
And then you can play around with the values, let's say today you don't want 10 picofarad, you want 1 picofarad. Okay, we can apply. Let me just put one side first. We can apply. Okay, I think not much changes. So you know that, changing to 1 picofarad doesn't change much. So these are some things you can play with. All right. I call it the design exploration stage. Okay. Yeah. So that's on the decoupling capacitors. And then as mentioned earlier, not just lump component, we have different modeling options for you to model your capacitors. So feel free to use any of the options based on the resources that you have for your simulation. Okay. And then one more thing is on some of the current density plot or electric field plots. Hopefully it doesn't look too long. All right, so this kind of electric field plot is useful to identify which part of your boards are having hotspots because at certain frequencies, let's say 100 megahertz, right? 100 megahertz, and then let me just change it to a possibly viewable feedback. All right. So I think now it's very clean, so it's all good. But this kind of electric field sometimes will help you to identify hotspots for your board, especially if you notice that there are some potential EMI issues. All right, maybe after first test, there's some EMI issues. You want to know where are the hotspots for the power rails. So this kind of electric field is good to know where are the hotspots across the power rail, and it might be good to start to change the power rails dimensions. All right. So we can look at E field, magnetic field. If you want to look at current density as well, that is also possible. Right. So different graphical tools for you to sort of identify this kind of hotspots over here. So I think the slide talks about it as well. All right. Looking at electric field, mainly is for hotspots for to mitigate any potential EMI issues over here. And then you can look at current density as well. All right, if there's potential heat and so on. So the last part is on, at least for AC analysis, is on decoupling capacitor optimization. What it does is that it optimizes the decoupling capacitors based on the cost of your decoupling capacitors, the number of decaps, and you can optimize based on the vendors. So it's more on the BOM list. All right, it's not optimizing the capacitor value. It's optimizing on the BOM list of the capacitor. Like let's say on your design you have 20. If I reduce to 10, does it still gives me the profile that meets my target impedance? Right, that's the goal. Right, so this helps you to save costs as well. Um, yeah, so we can look at page number 93. Okay, page number 93, it discuss with you on how you can actually do decap optimization, all right, to optimize the BOM list of your capacitor. All right, so we'll look at page number 94, whereby I right click on the AC analysis and it will show a decap optimization. So when the decap optimization is launched, that's where you can define, sorry, my display is a bit big, but when you right click and, select decap optimization, basically you will see a BOM list of your capacitors together with the target specification profile of your impedance. All right. So how do you define, what is the correct target impedance? You can go back to the slides. There are a few equations that guides you on, how do you define target impedance for your design. But I think if you look over here, so far it's low, so I think it's okay. So this is the target impedance profile that is labeled in the dotted line, right? So this is target impedance. And I think so far with my settings, everything is below target impedance. So I would say this design kind of pass. But in case you want to optimize the decaps, we can do that as well. Just click on optimize, and I think it will reduce more decoupling capacitors. All right, and then you can see whether you can reduce that to save costs for your design, right? Uh, yeah,
Is
so you can
is
see
this
the
the optimization is the optimization done automatically?
yeah done automatically, indicating to you the BOM list basically. So you can see instead of, I think I have 14 here, it seems that if I reduce to just 2 decaps, it will still meet the target impedance. So I can show the details. Okay, you can see that it still meets the detail, but of course it's not perfect. You have to check. This part is still picking, it's a little bit risky. So again, do check. It's not always 100% for sure is the best results. Sometimes you need to check. I think there's a Q factor ground. I think the Q factor is quite high over here. Q factor, I think, is related to resonance. Correct me if I'm wrong. But yeah, just check. Okay. If not, there are other options whereby just reducing to 5 decaps, you still get a low Q factor, right? Can show details. And yeah, this looks like a better plot, right? Using 5 decaps. Generally, it was okay. Q factor graph here's a bit high, but I would say it's better than the two lah, right? So maybe the second options might be better on that. All right. So mainly this optimization is on the BOM list. Okay, not on the
Mhm.
values, but the BOM list. Just take note on that.
Yeah.
Okay.
So should we avoid high Q factor? Should we?
I think we should. I think Q factor, I will need to check. I think Q factor is associated with resonance, which
Yeah.
we want to avoid resonance, right? So I think lower Q
Yes.
factor might be better, in fact, but
Okay.
I think
Okay.
this is something I will need to research as well, something interesting
Mm.
for me. Yeah, so I'll look it up and then I'll get back to everyone also. Yeah. Okay. So I'll get back to everyone on the Q factor. I think it's an interesting one over here. Actually, this is something new in our new release. Previously, they don't have the Q factor. So this is my first time seeing it also. So something I will read up on. Yeah. Okay. So this is on decap, so on optimization. And then as mentioned, we have the virtual component model. So place any virtual capacitors that you want to investigate. Does it help to improve the PDN impedance? Okay. Yes. So that's pretty much on DC and AC. All right. The last two part I wanted to go through is on thermal and also on electrothermal. Okay, which is part of the power integrity analysis. I might not have time to go through everything, but not to worry. We actually have a YouTube video right, to guide you through. But I would like to run through thermal, electrothermal, and I will use slide to present on dynamic sync because this is a very new feature that addresses the ground bound analyzer, the analysis of ground bound. So I'll touch on that. But I will start on thermal analysis. This is not on your slides, so you can just look at my demo, ask me questions. This demo, the same PandaBot demo is also on YouTube as well. So I will share the link. You can take a look. All right. So I'm going to kickstart on thermal. Okay. So I'm going to start on thermal analysis. All right. And the first thing I want to include is my thermal components. Okay. So I think my thermal components are U10. I think U10 is one of the SOC. Yeah, U10 is one of the SOC. If I look back at the slides, what is U10? Okay, let me just go back a little bit. Okay, if I go back to the main board, you can see that U10 is the main processor, I think. Yeah, the main processor that will generate a lot of heat. All right, so this on U10. Okay, so I'm going to include U10 and place it as my thermal component. Okay, and I think one more is U18, I believe. Yeah, let me just check. I think it's U18. Yeah, one of the audio system. If I'm not wrong, that is also generating some heat. All right, so basically, if you know from your vendors that those ICs are going to have some heat performance, you can do a thermal simulation using PI probe. All right, so once I've included, the main heat source component, which is this tool, okay, what I can do is I can double click and, I can model the thermal resistance performance of my ICs. If you have those information from your vendors, you can always include it in. Usually they are based on die to case top resistance, this kind of information. Okay, and then
Excuse me,
if that,
that's a packaging, yeah. Thermal properties of the package. Yes.
yes, correct, thermal
So,
properties.
what type of package? Specific type of package?
I think this one is generic in general. The main thing is as long as you have all this parameters, those thermal properties that you get
Yes.
from vendors, you can model them. So I think it serves a generic purpose.
Okay.
Yeah. Yeah. And then any heat sink or thermal pad that is from the ICs, you can include them as well. I think from cases whereby vendors don't provide them, if you know the material, basically we have, this kind of thermal resistance extraction tools. If you have those these materials like single die package or JDAC measurement, you have this information. It really depends on, yeah, I think JDAC measurements have some of the package that you can look at. Then it's able to extract the thermal properties. Yeah. So depending on what information you have, you can leverage on this to extract as well in case you do not have those information. All right. I would say these are some reference. It may not be the actual case, but it's a good starting point, I would say. And then for heat sink as well, what kind of material is being used for the heat sink, the thermal pad, you can model them. All right. So that's one. And then I think I need to define the thermal source property. Yeah. So depending on the source type, it could be a electric dissipation, heat source, and so on. If you need more details about the difference, I can share again. But for this demo, I think I'm just going to show on the heat source, which is I think 5 watt and 1 watt. Oh, sorry, it's the opposite. 1 watt, if I'm not mistaken. All right, and click apply and done. And then I can run the simulation on that. Have I run it? No. Okay. So yeah, basically you just have to model the thermal properties and know how the heat is being dissipated by the ICs. Basically, PI Pro will then generate a heat map for you to sort of analyze the heat performance across your board. Okay. So let me hope it runs quickly. Okay. So that's one. We can look into generating a heat map. And then another thing is on electrothermal analysis. All right. So electrothermal analysis is basically DCIR drop plus temperature effects. All right. So now we are including the thermal effects to see how it further affects the DCIR drop, because as we know, heat is going to affect DCIR drop for sure. All right, so the setup is still very simple. Just have to duplicate whatever you created initially for your DC analysis. You just have to duplicate it to the electrothermal analysis. And when you do that, I think you will identify all the components that are tied to that VBAT, if I'm not wrong. All right, so if I highlight all these heat performance component, it's a lot. Yeah, I think basically they include all, which is a little bit strange. But yeah, you can add in those thermal performance. And I think you can define all the resistant properties if you have those. So all these are done quite completely for us. All right, the thermal properties and of course any of the thermal source properties. All right, is it electrical dissipation, and so on. All right, all this you can model them. All right, and then once that's done, you can run the simulation. All right, and then we can look at the results. Okay, I think I need to run again. So let me just run the results. But I think the initial thermal map is being done. All right, so I can show you the heat map. Okay, so this is the heat map that you will get to see across your board. This gives you a better understanding of how heat performance will span across your board. All right. And then you can use certain reader marker to kind of read out what is the temperature across the entire board over here. All right. So anything near the processor is definitely going to reach as high as close to 100 degrees. That could be risky, not quite sure. Then therefore, if it's too high, then maybe that's where the heat sink or thermal pad comes in to help to reduce the temperature. Yeah. So this is some thermal performance that you can look at for PI Pro. Right? For electrical thermal, I think it's still simulating, but I think I have the slides results. Yeah, I don't have it, but basically, um, yeah, what the electrothermal does is that it combines both the electrical analysis together with the thermal analysis all together, and then to calculate how much voltage drop after including the thermal properties as well. Okay. So I think it's still simulating. But so far, any questions? Yeah, on PI Pro. Okay, so I think the results is done. If we look at the results over here, okay, again we can look at. Oh, sorry, it's still running. But any questions on PI Pro? Yeah, basically on power integrity. I think the
Is it
next.
also possible
Yes.
to simulate thermal in transient mode? So it's a function of time, how slow
Ah,
or how fast
yeah.
thermal change, temperature change is.
Yeah, so unfortunately, this is static, it's not dynamic, right? So I think you
Okay.
wanted to know as time passes, how temperature change. Unfortunately, it's not. This is static. Yeah.
Okay.
Mm. Okay. Any other questions? Yeah.
Yeah.
No
How about
worries.
I think this is based on natural convection, right? Natural convection without any fan. Is there
Ah,
any? Yeah, I don't
I
know. If we add a
good
fan,
point.
forced convection, what will happen?
Good point. So I forgot to mention about that. So for the thermal analysis, you can also specify what is the the heat flow,
Yes.
right? So I think natural convection is the one that without any fan, right? The heat will dissipate up or downwards. I think this is without any fan. But I think if you include any fan, this is where there's airflow that you force the fan to blow out the heat and so on. So I think basically you can set those how air is flowing across the board if you add any fan. I think fan will have some certain direction. Then you can specify the airflow speed to see whether does it help to reduce the temperature.
Okay, just fun, joking like question. I guess ADS is thermal analysis applies only on the surface of the Earth because the thermal convection is based on buoyancy force. It's related to gravity, right? Gravity on the surface of the Earth. How about
Okay.
the space electronic, where there is a microgravity? Then the
Hmm.
convection mechanism will not apply.
Yeah,
Yeah,
yeah.
is there any parameter that we can?
Hmm.
Yeah, okay. This is not a bit unusual equation, perhaps.
Yeah, but it seems like maybe if it's on space, because space is on different. You're talking about space, right? Just
Yes,
to,
gravity.
yeah,
Gravity is different. So
yeah.
because the natural convection works because of the buoyancy force, like
Mm.
the high temperature air will move. Yeah, it becomes lighter,
Yes,
right?
yes, yes,
And this work because of the gravity.
yes. Correct.
And without gravity, this will not work.
Yeah. So I think in
So,
space is a different thing.
yeah,
Yeah, it's a different thing, I think.
the question is
Uh,
whether NASA use your software or not. That's the question.
Yeah, that's a good question. Yeah. Yeah, something I can look into it also. That's interesting question because I think power integrity applies to our space related spaceship, right? There's thousands of data they need to process and so on. So yeah, I think that's something also I can look into. Interesting. Yeah. Okay, yeah, so I think the results is done for electrothermal. So electrothermal is just including thermal and see how the DCR drop changes. So again, definitely there are some changes, all right, for VBAT. I think if I compare it with the conventional DCIR drop, which I have already simulated, yeah, you can see that with the temperature, right? The one on the left is without temperature. The one on the right is with temperature. You can
Oh,
see
I
that
see.
there is more DCIR drop, right? So this is also the importance of temperature, how it can affect DCIR drop. And then the last part, I think very quickly, so the dynamic sync analyzer, this is something very new, which is to help on the ground bounce, which was one of the question. All right, so PCB with multiple power nets and ground are sensitive to EMI, which is caused by crosstalk or ground bounce. All right, so this is something that our PI Pro dynamic sync analyzer is going to analyze the impact of crosstalk and ground bounce between power nets. Right, so in this quick demo here, the test case here is that we have a low voltage aggressor power rail. All right, so this is the aggressor power rail, which have a 4-phase inductor. And then we have a sync, which is based on a 3-quadrant of U4. I think U4 is one of the FPGA, probably. Let me see from the previous slide. Yeah, probably is from one of the FPGA or CPU or something. And then this is the victim. The victim have a single phase inductor, VRM, package VRM, with 1 quadrant of the U4. All right. And then because to look at the net-to-net crosstalk separate from same net ground bounce, all right, basically what the simulator does is that it automatically behind the scene, you will add a benchtop ground plane. Right, so this is something similar to our conductor EMI. Maybe I can quickly show conductor EMI as well. We virtually add a ground plane for you. All right, so you don't have to do manual modification to the board. Right, we just do that ground plane for you, and then you can start to look at some of the net-to-net crosstalk or ground bounce. Right. So one of the I think key difference is now for ground bounce. We are looking at dynamic sync. All right, so that means we mimic the transient load step measurements, a repetitive pulse on off step load. Right, so this is needed. So we do support a periodic current pulse. All right, which is needed. And then because it's dynamic, for faster simulation, we use harmonic balance. Yeah, if you use the traditional transient, if it plots every single step size, it's going to take a very long time. So we use harmonic balance that computes in frequency domain, and behind the scenes, it applies the IFFT, inverse Fourier, fast Fourier transform. All right, so basically you'll get the time domain results very quickly over here. So this is something that ADS does behind the scene that speed up your simulation time. And then we have sync ports. I think this is something you have seen looking at the basically I think the current performance and the delta voltage between the power and the return ground net. So these are some results you can look at. Some of the setups, voltage ripple probes, basically is to do some measurements, okay, with this virtual ripple probes over here. All right, placing some points, some single pin measurement points on the board, and then you can do some measurements, sort of like ideal for separating ground bounce from net to net crosstalk, okay, to just separate the results. And then we can look at the results, looking at the aggressor's current, all right, and then of course of the victim current from the aggressor and the victims as well for the power rail, right? So even for power rail crosstalk, we are able to do some simulation. Basically, the dynamic sync analysis will show the crosstalk from the aggressor sync to the dynamic victim sync, right? How much is being crossed over to the victim. Okay, so power and gravity, few visualization again, looking at how the aggressors, all right, the aggressor is at the bottom, okay, how it actually coupled to the top part of the victim. This is something we can look at, all right? So victim power net, this is voltage versus time, all right? And then you can see how it actually affects, the aggressor power rail ripple, which is the red, all right? How it actually affect the victim power rail, power net, okay? So this is something that you can work with. Ground bounce, all right? So ground bounce analysis, this is also something that can be done with the dynamic sync analyzer in PI Pro. All right, so ground bounce is basically the noise ripple on a shared ground net caused by the aggressor return current. All right, so if you remember just now, this slide, we placed some voltage ripple probes. Right, so this voltage ripple probes where you place on your power rail. All right, it's just a simple power pins, like like EM simulation, just placing a pins. Basically, the voltage ripple probes will be able to simulate any ground bounce data. All right, so these are some of the ground bounce data that you'll be able to look at power net, right? From the power net, how much, there's some ground bounce on the ground net as well, the noise report on the ground net. Okay, so you can look at this kind of information. And then again, visualization helps you to locate the worst case location for the ground bounce issue. All right. So again, I think you can place different probes on the board and kind of look at the ground bounce effect at different locations. And then that will help you to sort of adjust your PCB design, all right, to see how you can reduce the ground bounce effect. Okay, so I can share this slide with you on ground bounce. I think this is working with Pico Test. We do work with Pico Test a lot for this kind of power integrity solutions or papers, all right, when it comes to simulation and versus measurement on that. Yeah, so that is pretty much on the ground bounce analyzer, and this will be included when you purchase our power integrity license. Okay, so this is on the PI dynamic sync. Okay, so sorry I didn't have that demo ready because it's quite a new feature that we just released. So I'm still preparing on that. But if you need more information, let me know. We can schedule a separate call to just go through on dynamic sync if it's applicable for your design work. And then I can quickly show you on conducted EMI. I think since we have time, just last one, I think. um, let me just quickly search for that. Conducted EMI. Let me see if I can find PI demo. Yeah. Okay, let me see if I have the, yeah, I have the semi. Yeah. Yeah. So in PI Pro, we also added conducted EMI for you to do any EMI analysis on your board. I think it does support both conducted and radiated, especially for CISPR 25 standards, which is coming from the automotive side. They are very strict, so we do create some of the compliance standards based on that as well. But you can see that we do set up the VRMs, okay, on the board over here. Okay, there are two VRMs. I think one is the connector. Sorry, one is the power connector, the main power supply, and then one is the voltage regulator. All right. And then we also connect with the sink. I think this is towards the FPGA of my AMD Xilinx board. All right, and then these are my simulated nets. Let me just hide everything. All right, so this is the entire power plane that I'm simulating together with, let me just highlight everything again. Okay, together with all the decoupling capacitors, everything that we set up. So everything that we learned earlier is also applicable on setting up with conducted EMI analysis. And towards the end, we set up the frequencies depending on your conducted EMI test. Any off-board options, you can see that we do support the CISPR 25 standards, which they have, I think, some cable length, which for the listen, so 6-inch, and then we do support radiated EMI as well. So once the simulation is done, I hope I have the results. Yes, I have. We can look at the switching nodes. Basically, let me just plot one. All right, we can look at the spectrum. All right, but we can also look at, for example, we can look at time domain response. All right, look at the switching volts at different nodes. All right, so this is one of the results you can look at. I don't think there is a mask tracer, but if there's any mask that you need to comply with, you can always add it in. That's for the conducted EMI, all right, looking at both the frequency spectrum. I think frequency spectrum, yeah, they didn't have the standards. But yeah, you can look at conducted EMI for both the frequency spectrum and the time domain. Okay. And then if we talk about radiated, I can show you as well. For radiated, we have enabled it, radiated EMI for CISPR 25. And then the results would be here. If I launch the radiated emission, all right, basically is having an antenna and then measuring the radiated emission. So I think it's loading a while. But basically, with the radiator emission, in our tool, you can rotate to different direction. Is it facing the antenna? Is it facing away from the antenna? Is it facing up? You can change to different directions and look at, whether does it have serious emission issues. Okay. So you can look at vertical polarization, for example, and then PCB and cable or only PCB, you can change that. Okay, I shouldn't have changed that. But you can see that, it gives you a pictorial image view from antennas, and then, you can start to rotate the orientation. So this is something that we do offer in our PI Pro license. So if you buy that PI Pro license, it will include this conducted EMI analysis as well. Yeah, so I think that's all for my sharing session for the workshop. Yeah, so I think in summary, I've gone through what are some of the tips and tricks to resolve SI analysis. All right, looking at the eye diagram, how do you identify whether there's crosstalk, there is a serious frequency dependent loss issues, how to work with equalizers. And then, of course, we've gone through a few labs on ADS, looking into very basic on how to run channel simulation, looking at eye diagram. Our channel simulation will support the different standards like PCIe, USB, HDMI, which is more for the SERDES. And then we also have looked into Memory Designer that is dedicated for Memory Designer application. I briefly talk about our standard driven like System Designer for PCIe, System Designer for USB. Those are also standard driven. We don't have time to go through deep, but we do have those standard driven. Yeah. But the generic one that applies all different standards will be our channel simulators. Um, then we look into SI Pro. All right, SI Pro, if you have a PCB board, how do you import it in? How do you set up simulation very easily with SI Pro, and how SI Pro being a hybrid solver can help you to save time, basically. Okay. Then we look into PI Pro, look at how to set up some of the things with power integrity related, like DCIR drop, PDN impedance, and then also looking at thermal and so on as well. Yeah. So I think that's the summary I have. Any questions from everyone here? I did take note the questions, so I think let me look it up on the questions and maybe I'll get back to Pak Isan, and then Pak Isan maybe
Okay.
can help to share with
Yeah.
everybody.
Okay.
I will also share with you some YouTube links. We do have a lot of YouTube resources that's available, so you don't have to worry about getting started with our tools. We have great step-by-step tutorials to help you get started with our tools. All right. And of course, any questions, just feel free to reach out to me. I think
Okay.
that's all from my part. Yeah. Thank you for everybody's time and attention for this workshop.